Hello friends, welcome to my YouTube channel. Friends, it is very easy to see that square root of 2 and square root of 3 are irrational numbers. But what about root 2 plus root 3? In this video, we are going to discuss the irrationality of root 2 plus root 3. First, let us check the irrationality of kth root of an integer n. We begin by showing, for the sake of completeness, that if k and n are natural numbers, with k greater than or equal to 2 and n not a perfect kth power, then kth root of n is irrational. In particular, square root of p is an irrational number for every prime p. Assume that kth root of n is a rational number in its lowest form. Call it a by b. Then, if you raise both sides to the power k and bring b to the power k on top here, so we will get this equation a to the power k equal to n times b to the power k. It follows that every prime divisor of n is also a divisor of a, because that prime divisor will divide right hand side here, so it will divide the left hand side, and being a prime it will divide a. And since a and b are relatively prime, that prime divisor will not divide b, and so no prime divisor of n divides b, since GCD of AB is 1. Consequently, the exponent of every prime divisor of n equals the exponent of that prime divisor in a to the power k, and hence it is a multiple of k. Okay. So, a to the power k is equal to n times b to the power k. So, every prime divisor of n is also a prime divisor of a, and so it is not a divisor of b. So, therefore, as far as exponent of prime divisors of n are concerned, b to the power k will not have any contribution. Therefore, the exponent of every prime divisor of n equals the exponent of that prime divisor in left hand side, that is a to the power k. And so, it is a multiple of k, because here every exponent is multiple of k. So, it follows that the natural number n itself is a perfect kth power, which is not the case. Hence, this quantity must be irrational. So, kth root of n is irrational. It is not difficult to see that the above argument cannot be used to prove that root 2 plus root 3 is an irrational number. So, we need some other machinery. So, we now state and prove a result which is essentially due to Carl Friedrich Gauss, and it states the following. So, we call it rational root theorem, and in short we will call it RRT. The rational roots of a monic polynomial, that means the roots of a monic polynomial which are rational numbers, and the polynomial is with integer coefficients. So, all such rational roots are actually integers, and each of these roots divides the constant term of the polynomial. So, I read it again. The rational roots of a monic polynomial with integer coefficients are all integers, and each of them divides the constant term of the polynomial. This is rational root theorem. So, how do we prove it? So, consider a polynomial like this, x to the power n. Coefficients are cn minus 1, cn minus 2 and so on up to c0. c0 is the constant term, n is a natural number, and these are all integers. c0, c1, cn minus 1 are all integers. Let a by b a rational number in its lowest form, that is b greater than or equal to 1 and GCD of ab is equal to 1, such that this rational number satisfies this polynomial, is a root of this polynomial. Okay. So, such that a by b to the power n plus c n minus 1 a by b to the power n minus 1 and so on up to c0 is equal to 0. Then, if we multiply throughout by b to the power n, we get this equation. All right. Therefore, it follows that this b, you see b is present everywhere here. So, b will divide a to the power n, and since a and b are relatively prime, b has to be equal to 1, otherwise any prime divisor of b will also divide a. So, a and b will not be relatively prime. And once b is equal to 1, then you see this equation once again, all these terms are divisible by a, b a. So, the last term becomes just c naught, c0. So, that also will be divisible by a. So, but then it also follows from the equation that a divides c0. This means that this a by b is actually an integer because b is 1 and a divides c0. So, that integer actually divides the constant term c0. So, that is the proof of RRT. Now, let us consider once again this number kth root of n, which we have already seen that this is a irrational number. So, using RRT we can reprove it actually. We can prove that it is an irrational number once again using RRT. So, consider this with k greater than or equal to 2 and n not a perfect kth power. Clearly, this particular number kth root of n is a root of the monic integer polynomial x to the power k minus n. Okay. So, if you raise it to the power k, it will be n. So, this will become 0. So, this is a root of this monic integer polynomial. So, by RRT, if this quantity were a rational number, it would be an integer. But if it is an integer, then what does it mean? That integer to the power k equal to n. Okay, this minus n equal to 0 means that integer to the power k equal to n. So, that means n becomes a perfect kth power, which is not the case. Hence, this kth root of n must be a irrational number. Now, we consider the irrationality of root 2 plus root 3. Let us put x equal to root 2 plus root 3 and square both sides. So, you get x square is equal to 3 plus 2 5 and then 2 root 6, and that implies if you bring 5 on the left and again square it, we get this polynomial. So, that means this root 2 plus root 3 actually is a root of the polynomial this one. So, if you bring 24 on this side and simplify it, so you will get this polynomial satisfied by this. So, this is a root of this polynomial. So, we can use RRT now. This is a monic polynomial with integer coefficients. So, by RRT, if this were a rational number, it would be an integer and it will divide the constant term of this polynomial, which is 1. So, root 2 plus root 3 will divide 1, means root 2 plus root 3 will be equal to either plus 1 or minus 1. but neither plus 1 nor minus 1 is a root of this polynomial. Okay. So this quantity has to be an irrational number. Okay. Now you can use this RRT to show that root 2 plus root 5, root 2 plus root 7, root 5 plus root 7 are all irrational numbers. Okay. Because if P and Q are two primes, so this root P plus root Q is a root of this polynomial. You can check it. So just put P equal to 2, Q equal to 5 and so on. And then P minus Q is equal to 3 square. So in the first case, you simply show that 1, 3 and 9 are not roots of this equation. And because x is present with even power, no need to check the negative powers. Okay, minus 1, minus 3 or minus 9. So you can check that this is not satisfied. It doesn't have a this integer root. Okay. So using RRT, we can show that these are actually rational numbers. So just try it. So hope this video will be useful for you, and thanks for watching.